In this final video on the atomic structure, or the evolution of the atomic structure, we're going to look at the contributions made by Niels Bohr. Now, Rutherford's idea of the atom being mostly empty space, it was, without question, the science proved this theory. But Rutherford only looked at those alpha particles. He looked at the protons, okay? Niels Bohr, on the other hand, was very interested about the concept of where these electrons go. Okay, he noticed that there was an actual pattern to where electrons should be within an atom. And he is the one who basically comes up with the idea of electron shells or orbits. Because until this point, you've got Rutherford, who, let's say we're going with an idea of this, assumes that these electrons are just randomly kind of placed here or there, okay? And there's no actual, pattern to it. But Bohr comes up with the idea that, wait a minute, yes, there are. There is a pattern. So Bohr improves on this model because he says, okay, I accept your idea of this positive nucleus, but I don't think that we have these random sort of, electrons do whatever you want. No. I think that every electron within an atom is going to have a specific place. And he called those energy shells or orbits, similar to how the planets orbit the sun. We have a set trajectory around the sun. If we didn't, we'd go crashing into the sun and we'd burn. That's not good. So all of these orbits, require a set amount of energy for those electrons to behave or to live on those orbits. And while those electrons are on their orbits, they're stable. They're not using excess energy. Life is grand. But every once in a while, electrons can get excited, or an excess of energy can be found within the atom, and it can cause those electrons to basically jump to an extra energy shell. So if this electron, and I'm using carbon, we're not necessarily saying carbon does this, but what would end up happening here is if this electron got excited, let's say if this substance was heated, because heat causes motion, well, this electron in this case would jump up to the next energy level. But here's the thing. That energy cannot be maintained, and at some point that electron comes back to its original stable shell or orbit. And when it does come back down, it's got to get rid of that excess energy. So what ends up happening is we give off different kinds of light. This is completely visible when you go look at fireworks. What ends up happening in a firework is inside the actual canister of the firework, so you've got all kinds of stuff. You've got chemical substances. And depending on what color you want your firework to be, when you light that fuse, so when that fuse actually gets lit here, and it burns up, when this gets launched into the air and it explodes, those actual atoms inside will react, and because they're heated during the explosion, when they come back down to their energy levels, the electrons in these atoms, they will give off certain colors. So case in point, things like strontium is an element in the periodic table. It is what creates the red of a firework. And we're going to look at a demo in class to show you different colors. What ends up happening when you heat certain elements. They will actually give off different colors because of that excess energy. So Bohr's contribution here is that, I still agree with the concept of that, positive nucleus, those protons in the nucleus, but I think that electrons they basically live on specific orbits. And we call those orbits energy shells. The first orbit has a maximum of 2 electrons in it. The second orbit has a maximum of 8. The third has a maximum of 8. The fourth, 18. The fifth, 18. And so on and so forth. We go up to 32 and then 32. Okay? So this is the Bohr, or actually it's called the Rutherford Bohr, because it's a combination of not only Rutherford's positive, nucleus idea, but it's got Bohr's little twist on it where you're talking about these energy shells. Okay? And there you have the progression of that atomic structure. Because we start off with this solid, impenetrable ball with Dalton. And then, through experimentation, we stick with this solid, impenetrable ball. But we add negatively charged electrons into said ball. And this is Thomson. Okay? Then we progress, and through the gold foil experiment, we come up with the idea that the atom has a very tiny, tiny center. And I mean, the example they're giving is that the nucleus of the atom is the size of the tip of my pen in the center of, let's say, the Bell center. The rest of that space is empty space where the electrons live. Okay, so then we have this kind of idea that the electrons are just going every which way, and this is Rutherford. Okay. And then finally, what we're going to be looking at is the improved version of Rutherford, where, yes, we agree with that positive nucleus, but the electrons are not just wishy-washy added wherever, they're actually living at specific locations within the actual atom. So 2 on the first orbit, and then, a maximum of 8 on the next orbit. So I hope you have a better understanding of how the evolution of the atom has occurred.